I'm Omar Nagar presenting my research on in-bed human pose classification using sparse inertial signals as part of the University of Liverpool Doctoral Network in AI for Future Digital Health. My team comprises of experts in engineering and computer science, collaborating with an orthopedic consultant at University Hospital Aintree in Liverpool. Um, It's been almost a year since my family doctor told me I have been sleeping in unhealthy positions most of my life. Uh, if you feel good at night but wake up in the morning feeling backache, neck pain, numbness, you name it, then you're in the right place. Yeah, just as you heard it, in the right place. You better not visit a clinic because honestly, doctors have little to offer unless you're happy with an uncomfortable night splint or a little surgery. You can sleep on the most expensive mattress or the most comfortable pillow and yet suffer from a musculoskeletal disorder at some point of your life. Bad sleep does not only cause pain, it's commonly linked to complications with breathing, poor blood circulation, syndromes, and more. I'll start off by presenting the gap that my research is trying to fulfill, then I will illustrate how that is being accomplished and the results which have been arrived at in the course of this work. Finally, I will leave you with a concluding summary, future work directions, and a list of key references. First, the research motivation. Why would someone analyze human motion? Um, Actually, why not? When biomechanical analysis helps Olympic runners optimize their performance by a fraction of a second, or when gait analysis gives us new insights into designing biomimetic lower limb prostheses, or when CCTV systems can detect abnormal human behavior just by simply looking at moving people, or when the entertainment industry uses motion capture for video game characters. In the big research field of human motion analysis, there are two main directions: movement quantification and classification. Quantifying the body movement involves the study of the kinematics of selected body segments. The movement classification looks into the different categories of assessing one's quality of motion, hand gestures, whole body postures, and daily activities. Within this big picture, the proposed research addresses a post-classification problem for a healthcare application. Now let's look at the problem more closely. I want you to imagine it's nighttime, but please don't fall off to sleep yet. Uh, and you're given a sleeping pose monitoring technology that should track your in-bed body poses overnight. With this information in hand, we will be able to identify the risk of developing musculoskeletal disorders associated with certain sleeping poses. In the literature, a number of works address a similar problem. Among the non-wearable solutions, the pressure-sensitive matrix provides a tactile image revealing the body weight distribution over the surface area of the matrix. This allows for a reconstruction of the body pose in bed. With the recent advancements in imaging technologies and visual data processing, infrared and three-dimensional cameras have also been used to capture people sleeping in bed and estimating their body pose accordingly. Now let's cover the wearable solutions. Out of the all wearable devices, inertial sensors are the most relevant to the problem in hand, since they quantify the underlying kinematic motion of the body segments they are attached to. On the left of the slide is an example of a work that used wearable sensors to recognize 4 standard sleeping poses. Another example is now shown on the right side, although in this study the authors have considered basic poses out of bed. The authors used a dense network of inertial sensors, I think over 30 sensors, distributed over the body to classify its pose with limited training data. Certainly, the aforementioned solutions have their own limitations and drawbacks. Let me illustrate to you what the main challenges are. Based on our earlier categorization of existing solutions, the limitations differ between wearable and non-wearable systems. Generally speaking, with non-wearable solutions, the absence of wearability translates to reduced body observability, which in return induces more uncertainty on the body pose. For example, UV covers often result in occlusion-related challenges to vision-based systems. In the case of pressure-sensitive matrices, it is likely also that one or more body segments might not be touching the bed at some specific poses. In addition, many of us feel uncomfortable in front of cameras. Knowing that this happens when we're awake, you can imagine how awkward it would be to know that someone is watching you overnight. For the wearable solutions, although they enjoy potentially more body observability depending on their distribution, their intrusiveness remains a challenge. Additionally, determining the orientation and position offsets between the sensor and body segment frames is a whole new task by itself. Another typical constraint is the scarcity of labeled inertial data, which is potentially one of the main reasons why we often end up having poor generalization performance on unseen data. Among the reported works on sleeping pose classification, they mostly considered the 4 standard sleeping poses: supine, prone, left and right lateral positions. Since healthcare systems need more detailed representation of the human body pose, such a coarse classification is insufficient. In this work, I can say we have managed to overcome the last 3 limitations. Now I'll be presenting the methods and main findings of our research. It was critical to validate the proposed approach in a simulation environment before going for the clinical trials, which we're working on at the moment. Shown is the workflow of the presented work, for which we took every care to emulate a realistic framework. In stage 1, we modeled the salient features of the human skeleton within a computer graphics software. This included defining the body segments connected at joints with their respective degrees of freedom and constraints. Then we manually animated the character model to iterate over a closed set of sleeping poses. Subsequently, we exported the necessary kinematic information for tracking certain body segment orientations. In stage 2, as in reality, we found that the animation clip provides scarce data that is insufficient for training a machine learning algorithm. We therefore introduced new augmented segment orientation data to our training dataset. With the resultant enhanced training dataset, we then implemented a multi-class classifier in stage 3 to map the segment orientations to the set of sleeping poses. Finally, the most likely sleeping pose is selected based on a selection criterion. Next, let me illustrate to you how this is being accomplished on a lower level. On this slide, the major steps that took place in stage 1 are presented. Upon discussions with our orthopedic consultant, we have expanded the study to include the 12 sleeping poses shown on the left. Then we have created the alien-like character model in an open source software called Blender, which we have animated as being displayed now to perform all of the sleeping poses separated by an intermediate calibration T-pose. It has been agreed that we will only consider tracking the 4 extremity limbs, both wrist and ankle joints, for the classification problem, unless more observability of the body pose is deemed necessary. As a prerequisite for the segment orientation tracking, we leverage on a functional calibration procedure at each one of the extremity limbs to determine the anatomical axes of rotation at each joint. Then we export all these kinematic information in a BioVision hierarchy BVH file to MATLAB, where the actual segment orientation tracking takes place. Enlarged on this slide now, we can see how we're able to track the left wrist joint. We refer to it as a child frame with respect to Blender's global frame, referred to as a parent frame in this context. Just to note, the kinematic representation used throughout this work is the axis angle representation as displayed at the top of the MATLAB figure. In this slide, you can watch the simultaneous tracking of the 4 extremity limbs as the animation takes place. Unlike many of the works in the literature, our proposed segment tracking algorithm refers the orientation of each extremity limb child frame to its parent segment frame, in our case, the forearms and shanks. Now, being able to track body segments with the axis angle representation, we need to gather more data to effectively train our classification algorithm. For this purpose, we propose a jittering-based data augmentation technique, which involves the addition of Gaussian noise to our representation. Apart from the scalar angle, we have realized that simply adding noise to the Cartesian components of the axis of rotation can result in significant changes in the overall limb orientation. Therefore, our novel data augmentation technique passes through an intermediate spherical coordinate system, in which the axis of rotation is parameterized by 2 orthogonal angles instead. Adding Gaussian noise to these 2 angles is ensured to produce bounded orientation changes. The addition of noise is performed by sampling a zero-mean Gaussian distribution with a unique variance for each noise hyperparameter. In the bottom left figure, you can see how we managed to produce 100 new augmented axes of rotation, taking a concise cone shape. Motivated by their high performance across different applications, support vector machines have been chosen for the classification stage. Since SVMs are originally suited for binary classification problems, therefore an error-correcting output codes model, shortly known as ECOC model, is employed. As observed from the block diagram of the ECOC model illustrated on this slide, it first breaks down the 12-class classification problem into a set of binary classification subproblems, each handled by a binary SVM learner. Then the vector of combined classifier outputs is compared against the reference code word associated with each of the 12 classes using the Hamming distance measure. The reference code words, as well as the binarization of the multi-class classification problem, is based on a coding step that is the first step of constructing an ECOC model. Finally, the predicted class is assumed to be of the minimum Hamming distance. All the hyperparameter values within this system are optimized using the Bayesian optimization algorithm. On this slide, you can see all the hyperparameters used in the proposed approach, which have been grouped based on the algorithm they belong to. For the jittering-based data augmentation technique, we have the 2 real-valued variances of the Gaussian probability distributions from which we're sampling. Also, to overcome the nonlinear separability of data, our SVM binary learners employ a kernel trick to transform the kinematic input data to a higher dimensional space in which it would become possible to separate classes with a hyperplane. The type of the kernel used is a categorical hyperparameter that needs to be optimized. In this work, we consider 3 possible options: linear, polynomial, and Gaussian kernels. Moreover, we use a soft margin formulation for our SVM learners to make the classification algorithm robust to outliers, potentially due to noise contamination. Looking at equation 5 in our paper, a slack variable called gamma is used to ensure the SVM constraint is satisfied in the presence of outliers. To avoid using values of gamma that are too large, an additional L1 regularization term is introduced to the cost function of the SVM optimization problem. However, this would require an additional constraint on gamma itself to ensure it always stays positive, since it is a minimization problem. Lastly, a scalar hyperparameter C is used to control how much the aforementioned L1 regularization term contributes to the cost function. Lastly, as it has been mentioned earlier, the ECOC model breaks down the multi-class classification problem to a set of binary subproblems by assigning a reference code word to each class to be matched later with the combined classifier outputs. This coding step involves the construction of a coding design matrix where each row represents the reference code word corresponding to each class, and each column represents the class assignments for each SVM binary learner. In our work, we consider two coding designs. The first is the one against all coding, where each binary classifier takes in only one positive class and treats the rest as negatives. The second is the one against one coding, which considers all class pair assignments by allowing each binary class to take in one class as positive and another as negative, while ignoring the rest. The ECOC model performance was evaluated on several augmented datasets produced given different hyperparameter settings for the proposed data augmentation technique, primarily controlling the levels of added noise. The mean and standard deviation of the post-classification accuracy were regarded as primal performance metrics. As it can be seen, the system generally maintains high generalization performance, as high as 100% classification accuracy with minimum or minimal deviation levels, despite we have tested levels of noise that are beyond what is usually encountered in reality. Here in this section, you will find a concluding summary of the presented research, directions for future work, and a list of key references for further reading if you would like to. Thank you for your attention. I hope soon my ongoing work towards clinical trials will develop into a commercial technology which will enable us to wake up ready to tackle the day. So stay tuned. I'm more than happy to have your questions now.
Thank you very much, Omar. Any questions, please? Yeah. For Omar. If you have questions, you could post them in the chat or raise your hand. One from you, Omar. So did you consider other approaches to generating the data? Because of course, you, in terms of the augmentation approach, were there other approaches that you considered as well?
Well, as I mentioned in the jittering-based data augmentation slide, we first tried the manipulating the Cartesian components of the axis of rotation by adding a noise to them, but it turned out that it's not a really wise thing to do, because it can cause unbounded changes in orientation that are undesirable. So the next step was to go on with the spherical coordinate system trick, which worked pretty well for us so far. So I would say it's interesting, but honestly, there is no motivation to go for another another technique or try it right now, unless in reality we come across, when it comes to the clinical trials, which I hope it will take place very soon, unless we come across some problem, then if the solution was to try another data augmentation technique, surely we'll go for it.
Okay, no, I was just wondering whether your specialists or clinicians have been, I've had a chance to comment on the way you've generated a data set. Yeah. Before going into the trial, have they had a chance to have a look at your data sets and reassured you that it's what they will be interested to use going forward?
You mean whether the data set will be suitable
yes,
for the actual data that to be gathered in reality?
Correct, yeah.
Well, this is now a track of matching the technology or the firmware on the wearable sensors that we are currently developing, and whether they will be compatible with the approach that we have proposed in simulation. So so far in the I would say the imagining the flow of work so far that we have gone through, we tried our best to use standard kinematic representations that can be easily obtained from commercial IMU sensors, for example. So I think by far there should be no problem obtaining the same type of data from commercial sensors. But it's again a question of whether the machine learning algorithm will be robust enough to maintain the high performance obtained in simulation.
Okay. Yeah. Thank you very much, Omar.
Thank you very much.
We'll now move to the next paper in the session, and again,